Okay. So today we're going to do a little bit more with understanding and proving the zipper theorems. Okay, so I put some pictures of them up here, and I will recall them on the board here. So first, let's do number 2, theorem 1.2, for the quantum gravity case. So what is this saying? Okay, so again, the idea is I'm going to fix this kappa bigger than 0. And mostly with pictures, we'll deal with kappa between 0 and 4, although the theorem works for other kappas. It just has a different interpretation. And then I'm going to let a to t be the segment of SLE kappa generated by this reverse Loebner flow. So I'm just going to do a zipping up by reverse Loebner flow up to some time t. And I'm going to define this Q and this thing which is a martingale. And then I'm going to say these things agree in law. One of them is I just take h0 plus h tilde. And the other is, well, maybe let me write this over on this side. It's the same law, but so one is I just take h0 plus h tilde. That's one way of constructing a random surface. The other is I take h0 plus h tilde, I draw a little slit, an SLE slit, and I unzip it. Okay, that's another way of constructing a random surface. What I want to say is that this random surface has the same law as this random surface up here when you forget about the line. So in law, this is the same as this. Another way of saying that is that this random surface I construct with h0 plus h tilde is stationary with respect to the following Markov transition. Okay, the transition is I give you this random surface, you draw an SLE, and then you unzip it. Okay? So that's just a clean way of thinking of what this means. And I could imagine drawing the SLE all the way to infinity, and then this thing would be invariant under unzipping and rezipping and so forth by a capacity unit. Theorem 1.1 is essentially the same. Just the same thing, but it's a slightly different formulation. In this case, we're taking 0 boundary conditions or fixed boundary conditions instead of free, but we're still saying that a certain couple of things agree in law, which is basically you can take your h naught plus tilde h over here. In this case, this is a 0 boundary free field. Here it's the free boundary free field. In this case, what I'm saying is instead of drawing an SLE and unzipping and saying I get something with the same law, I'm basically going to draw an SLE over here and zip up. So I'm saying taking this AC surface and zipping it up by t units gives me a new AC surface with the same law as the original one. I just take this one, I zip it up by t units, I forget about the line. So I map from this picture back to this picture, I erase this line, and then I have an AC surface with the same law as the original one. So in both cases, it should be thought of as a sort of stationarity thing. It's telling me that this particular random surface is invariant under a certain Markov transition. In this case, the Markov transition is draw a piece of SLE, unzip. In this case, the Markov transition is take this guy and zip up by some SLE. Okay. And in both cases, there's something natural you could do, which is to just if I just extend this flow line all the way to infinity, then what I can view this is there's an AC surface on the left and AC surface on the right, and I'm just zipping the two together, unzipping the two. But the thing is here, in order to decide how to zip up, I need some additional randomness, because in order to get from this picture to this picture, I had to generate this, decide what this curve here was. And I just generated from an SLE. So in order to zip upward from here to here, I needed additional randomness. Okay, but in order to unzip, I don't need any randomness in the AC case. Okay, what happens on the quantum side? Well, the quantum side, I can do the same thing. I could just extend this to an SLE. And here there's something different here. In this case, by this Julien's result, we know that if I really know the whole field, it determines this path. So once I draw for you all these arrows, this path is just there. You know, if I were smart enough, I would be able to just construct it from given the field. So the path is just there. On the other hand, I need new randomness in deciding how to zip up. Over in this picture, this path is not determined by the field. I just drew this as an SLE independently of the field. So the field is there, and I just independently drew this SLE there. Okay, and now I'm still saying I want this thing to be invariant under zipping up or zipping down. But in this case, of course, zipping down is deterministic. I just do the Loevner flow for this path. But zipping up is also deterministic because I have this fact that we're going to prove eventually, which is that these lengths, the boundary lengths, will match up. So when I zip up, which points get mapped to which other points in the zipping is determined by the quantum length measure on this, the plus and minus real axes. So there are some subtle differences in the two pictures. In this one, there's extra, the curve, in order to generate the whole picture, you need to use some extra randomness to generate this curve from 0 on to infinity, because it's not determined by the field itself. And in this picture over here, this curve, 0 to infinity, is determined by the field itself, but you need extra randomness to decide how to zip up. So in some sense, in this field, the future of the path is determined by the field. And in this picture, the past is determined. The way you zip up, the stuff that's not zipped up yet, is determined by the field. Okay. So maybe, before I go on, I will just take maybe 5 minutes of questions about this statement. And then we're going to plunge headlong into proving both of these things, and we'll do them both together, side by side. So let's have some questions. Yes? Yes. That's right. That's right. So he's saying that here, if I wanted to go from this picture back to this picture, so, okay. So let me say again how I constructed these two pictures. In this picture here, I chose this field, H0 plus H tilde. H tilde was a free boundary Gaussian free field. H0 was this deterministic function. It's the log of z times this 2 over root kappa. So so that's how I generated the field, and then independently, I generated this white line up to some time t as an SLE. So this here is SLE. This here is free boundary GFF, and this H naught is minus 2 over root kappa times the log of the absolute value of its argument. Okay, so that's what these various pieces are. So this SLE is generated independently of this. And I generate it up to time t, and then given it up to time t, I may as well just draw a little green line that goes on forever after that. And just the rest of the SLE. I'm not going to use this green part, but I just drew it. Okay, over here, I took the quantum surface and I unzipped it. So I took the conformal map, normalizing map for this curve, and I just mapped over the quantum surface with the transformation rule. And I got this object over here. And so then my claim was twofold. First of all, what this theorem 2 just says is that this picture has the same law as this picture. Well, it's sort of obvious that in both pictures, this thing is an SLE, and it's independent of the curve, of the field. That was just sort of true by construction. Here I forced it to be independent of the field. After I unzip, well, I mean, this green thing, just by the Markov property, it's still independent. It never cared about what the field was. So in both cases, the path is independent of the field. And then the claim is that if you look at the field itself, it's the same. In particular, if I think of there's a quantum surface on this side, a quantum surface on this side, I'm just, when I go from here to here, I'm just zipping those two quantum surfaces together. When I go from there back to here, I'm unzipping them. There's a corollary to this that I showed a picture of here, which is that if I just sort of define, if I kind of define, I take this object and I take the independent SLE, so exactly this picture here, and I define D1 to be the thing on the left, the surface on the left side of the path, and D2 to be the surface on the right side of the path. So HD1, HD2 are the restrictions to the two sides. Then what happens is that if I just define these quantum transformations, so here this just, don't worry about the notation, it just means zipping up or zipping down, then I find that the law of this pair of quantum surfaces is invariant. So focus on the picture here. Here I've taken this picture and I've put some dots on it such that the length between each pair of successive dots is the same. So it's a unit length from here to here, a unit length from here to here, unit length from here to here, unit length from here to here. And it's also a unit length from here up to here. And again, that's subtle because when we initially defined quantum length, we did it on a real line. But if I have a curve, I can always do the conformal transformation that takes this back to a real line, and then you use the coordinate change rule and then compute the length down there. So I just have these dots evenly spaced in terms of length. Okay, now I think of this like a zipper on your coat. Right? It has various things that clasp together and that unclasp. So I have the little zipper thing down here, and when I can zip these two sides together, this will get matched up with this will get matched up with this will get matched up with this. Or I can unzip. I can pull this down, I can pull this apart. And what the theorem says is that this is a pair of quantum surfaces. Each one has infinite area, total area. The stuff on the left, the stuff on the right. And as I zip up by unit of capacity or zip down, the law of the pair remains unchanged. Okay. So that's the statement. So yes, another question. A generator form for the invariants. Yes. It's a group. I can go both directions. Yeah, I mean, I don't know. That's how you prove it, you say? I mean, in some sense, it's there. Yeah, I guess you could do it that way. I mean, when I actually, write this down, what I'm going to say is something that kind of amounts to that. I'm just going to draw this curve, look at the conditional law given this curve, and show that it. Well, I'm just going to fix one test function, one smooth test function, rho, and I'm going to look at the law of h integrated with rho over here, and the law of h integrated with rho over here in the two pictures, and I'm going to show that those two things have the same law. So if you like, I'm just focusing on one test function at a time. And then when you talk about generator, well, you can look at, how does the expectation of this particular function evolve as you zip up or zip down. And that's what we're going to be computing explicitly. Yes? Yes.
You get this thing on the left, and the consequence of that is that if you start with the guy on the left, you can reconstruct the guy on the right, because there's a way to reconstruct it. I've always shown you that the way to reconstruct it is constructed before, and if there were two of them, then they would have necessarily to be unique. Right? So in general, you don't know that there's a welding.
Yeah, that's right. That's right. So what Mendelin is asking is for me to just do a reminder of theorem 1.3 and 1.4. And so 1.3 is saying if you look at this construction and I look at a point, say this point here, I call it Z, and I look at its preimage down here, and I call them Z plus and Z minus, then the length of this interval from 0 to Z plus is equal to the length of this interval Z minus to 0. And so in other words, the quantum length measured from the left side is the same as the quantum length measured from the right side. So that's that theorem. And then this theorem 1.4 is the one that essentially follows from the work of Stoss and Jones, together with the known results about SLE by Rhoda and Schramm and others. So, and this is telling you that basically there's only one way to, once I tell you the homomorphism, I tell you which curves match up to, which points match up to which other points, there's only one way to zip up. And the idea is, if there were another way of zipping up, then I would have a map where I say, zip up one way. I could start up here and say, zip down, and then zip up the second way. And what that would do is it would give me a continuous homeomorphism of the upper half plane, which was conformal except along this line. Made something funny is happening on the line itself. Everywhere else it's a conformal map, and it's a continuous homeomorphism. And it takes infinity to infinity with the right normalization. It looks like the identity near infinity. And this theorem of Jones and Smirnov tells us that the only map that does that is the identity. And in the complex analysis world, that is statement is equivalent to saying that this, by definition, is saying that this curve is removable. So the curve is removable if there's no way to take a map from this half plane to itself that looks like the identity near infinity, and it's continuous everywhere, and it's conformal off of the curve. Okay, that doesn't exist. And because of that theorem, we know that once I tell you how these things zip up, it's unique. There's only one way to do it. So the curve is determined by the field. Okay. And that's, let me just state very briefly, yes? Okay, yes. Yes, so we're in this picture of 1.2. Okay, fine. Yes, so once we go from the right to the left, yes. Yes, because the field you obtain over here is still just a Gaussian free field. Yes. Well, what I'm claiming is, if I look at the length of this segment here, okay. Yes. Right. So remember what. So I should be careful. When I say I am mapping back, what I'm actually doing is I'm mapping back, and then I'm adding the log of the derivative times q. Because I'm doing a coordinate change of the random surface, of the quantum surface. Whenever I do a coordinate change, remember, if I map a quantum surface to another, map one domain to another, if I want the measures of the image to be the push forward or the measure on the thing I start with, then I can't keep the same h. The h is more than just composing. I have to add this q times the log of the derivative. Yes, that's right, that's right. Okay, yeah, that's right. So it's not, this curve here is independent of this field here, but when you unzip, you're adding q times the derivative on this side and q times the derivative on this side. And that's sort of, a little thing on this side will get stretched out by the map, something on this side will get stretched out by the map. But I'm adjusting both sides by adding q of the derivative so that the measure down here is equal to the measure over here. So, if this curve, imagine this curve is smooth, or even piecewise linear, then I take a little segment here, a little segment here. When I unzip, they get mapped to a little segment here, a little segment here. And when I unzip, I add the log of the derivative times q in this case, the log of the derivative times q in this case. And because I've added those two things, both of these things have been stretched out by different factors, but I added things to compensate so that the lengths are still the same down here. Yes? Uh-huh.
The way you go back is that you say that the SLE is a unique number curve with that regularity that such that that's the idea.
Well, the idea to apply Smirnov-Jones result, what I do is I mean, the curve is given. I have one way of zipping up.
But I'm saying, what you're saying is that the curve is given, and if there would be another one, like so you say.
It's not just, I mean, what they prove is there's no other curve at all that does the job. It's not that this one's holder and any other one has to be weird. It's that, if this one's holder, there's no other one at all that has the right zipping up. Okay, so hopefully, people understand the things. So there are basically these, just these few results that we're doing in this paper and in this course. There's theorem 1, theorem 2 about zipping. Then there's this this thing that the lengths on the boundaries match up, and there's a unique way to unzip. That's 1.3 and 1.4, and there's that corollary, which really didn't have any new math content. It's just a different way of phrasing it. You're stationary under zipping and unzipping, and there's one other corollary that I don't know if I will actually get to proving in this course, but I want to just state, which is, and that one other corollary is this length stationary. And I just want to say quickly what it means. So, well, in fact, maybe don't even worry about reading what's up there if you don't want. I just wanted to say there is a way of setting this up so that instead of being invariant by zipping up by a unit of capacity or zipping down by a unit of capacity, it's invariant under zipping up by a unit of quantum length. So I can construct a different version of this picture where if I zip up by one unit of quantum length or down by a unit of quantum length, the law is invariant of the pair of surfaces. And so, I have a pair of infinite surfaces. They're glued together. There's some notion of length along their boundaries. The pair of things are random. I can zip up by unit. I can zip down by unit. And the miraculous thing that happens for this pair of surfaces is that if I look at the thing on the left as a quantum surface and look at the thing as the right as a quantum surface, those two objects are independent of each other. So I'm really taking two independent quantum surfaces, each with a marked point and a marked point at infinity. I'm gluing them together along this path, and then I can zip up or zip down on the other path. Down here, I can zip up or zip down, and it's stationary under doing that by a fixed amount. Okay, and the reason I state this version is that I want to tell you a discrete version of it, just so we have this picture in our heads of why something like this should be true. Okay, so what I'm going to imagine now, I'm going to go to the setting of this discrete world, and I'm going to take a random graph together with a spanning tree on the graph. So here, well, it's not exactly a spanning tree, so what have I done? It's a random graph together with all the edges on the boundary being included and one chordal line being included from two marked points, A and B. And then, and the rest of the graph I have, so this is sort of a figure 8 thing I get by taking the whole outer boundary and this one chord. And then basically I have a uniform spanning tree rooted at that figure 8. So every vertex is connected by a path to the figure 8, and there are no cycles except what you get from the figure 8 itself. Okay, so a natural thing to ask is, what happens if you somehow choose choose uniformly among the set of all figure 8 pictures that look like this. All planar maps, all spanning trees with a pair of marked points, the figure 8, and spanning tree and the rest. So there's some finite number of ways of doing this. If I say, and now let's say I'll fix the total number of edges, and for technical reasons you needn't care about, I will, or maybe you will care about, I will count the outer edges as half an edge. Okay, so I fix the total number of edges, except that the outer ones each only count half. And I draw this picture. I choose uniformly at random from all pictures like this, with n edges. Okay. What's that? No restriction on the degree of the faces. No, any old thing I want. Okay. And now, I'm going to take this picture and conformally map it to the half plane in a way that A goes to 0 and B goes to infinity. Now you might ask, well, what do you mean by conformal map? Because you haven't really put a metric structure on the inside of this yet. And the answer is, well, put any natural metric structure on the inside that you want. But it should be one where each edge has length 1, say. I mean, there's one sort of canonical way of doing this, which is to replace each edge with the unit square, where the unit square has one vertex for each endpoint and one vertex for each face. So that's shown here. There's one canonical way. If I give you a graph like this, you can put a new vertex in the center of each face, and then for each edge you get a unit square, which is you connect its two endpoints to its two dual endpoints, and I think of this as a square, and I think of all these squares as being unit squares. And now you see why the edges on the outside only count as half, because I'm just taking this to be now half of a unit square. Okay. So if I do that, then that gives me a metric space structure. So I can view this as a manifold, random manifold with a curve on it. It's a manifold obtained by gluing together all these unit squares. And now I just conformally map it out to here and see what happens. Well, this curve will get mapped to a path going from 0 to infinity. And now I'm going to claim that as I take this total number of edges large, I take n to be large, that it should be the case that this converges to a scaling limit. And how would you talk about what this scaling limit was? Well, first, if I take the area measure up here and pull it down, I should get some area measure over here, some random area measure. If I take the length measure on the boundary here, it should pull down to some length measure on the boundary here, and also a length measure along this curve. And if I, well, okay, so those are the things that I should have in this picture. The scaling limit, I should have some sort of an area measure, some sort of a boundary length measure, some sort of a length measure along the curve, conformal embedding. Now, what things would we expect this scaling limit, what properties would we expect it to have? Well, we would expect, well, first of all, let me say, phi a goes to 0, phi b goes to infinity, that doesn't determine the map yet, right? Because I still have a scaling factor. But let me just fix that scaling factor in some way. Maybe I'll take a unit ball here, or a semicircle here, and I'll require the total area of that semicircle to be 1. Or maybe I'll divide the total area up here by k, and then require the area down here to be 1. So the area down here contains the equivalent of k unit squares worth of area from up here. And the idea is I'm going to take k to infinity and n to infinity in such a way that n over k gets large also. So I have a large amount of unit squares mapping to this unit circle, but the set of area that maps to this unit circle is a small fraction of the total area. Okay, so that's, and it should be that, if I normalize whether the area within this unit circle is 1, I get a scaling limit. Well, if the area in here is 1, just compactness, I know there's going to be some limiting law for the area measure down here within this semicircle, at least subsequentially. So I get some random measure. And I want to say there's also a random length measure on the boundary. And the question is, in this random measure, what should the curve be? Does anyone have any guesses what that curve should be? SLE2. Yes. We have someone making a bold guess. This is what I think also. So it's not a proof, but at least 2 people in this room believe it. Sort of the reason is, well, I know that if I do a Brownian motion up here and conformally map that, it's going to be a Brownian motion down here. Brownian motion is conformally invariant. If I do a Brownian motion on the manifold I get up here by gluing all those squares together. So Brownian motion is invariant. I kind of suspect that if I do a simple random walk on this graph, it's going to look kind of like a Brownian motion. Usually simple random walks look like Brownian motions. Well, if the random graph is really weird and a walk on the edges is really different from a Brownian motion on the faces, maybe you can cook up examples where that doesn't work, but all the weirdness should kind of average out because things are random, and it should just work. The simple random walk here looks like Brownian motion. And loop erasure of Brownian motion is SLE2. This is Da-Peng Zhan's result. So it should be that loop erasure of simple random walk is SLE2. And there's actually, Yadin and Yehudiyaf, did I say that right? What's that? That's what I said. Yadin and Yehudiyaf. That's right. So they have a result that says if you take any graph on which simple random walk looks like Brownian motion, so there's a planar graph embedded in a way that simple random walk looks like Brownian motion, then if you do the loop erased random walk, it looks like SLE2. So we have not a proof, but fairly compelling heuristics to suggest that if I condition on the graph, I let the whole graph be fixed, and then choose this chord, it should be an SLE2. Well, when I look over here, what does that mean? I'm conditioning on the area. If I condition on what the graph is, then it really determines for me the area measure down here. So I'm conditioning on the area measure down here, the surface measure. Conditioned on that, the path should be an SLE2, which means that the randomness in the path and the randomness in the area measure should be independent in the scaling limit. So I would expect, if I take the scaling limit of this, then this path should be independent of the random metric. Okay, what else would I expect? I expect that what happens on this side is essentially independent of what happens on this side. Why? Well, think about it. If I condition on the length of the outer boundary and the length of this curve here, then and the total size, the total number of edges on the two sides, once I condition on those things, what happens over here really is independent of what happens over here. In fact, it's really enough just to condition on the length of the boundary and the number of edges on this side or the number of edges on this side. Condition on that. This is independent of this. And so you kind of expect that when you zoom in near a point, any randomness coming from the total length of this path sort of becomes independent of the behavior near this point. And so you should get that if I just look near this point, what happens on this side, just as a surface, is independent of what happens near this side. So I really think that in the scaling limit, the random surface on the left and the random surface on the right should be independent of each other. And the next property you would expect is, look at this picture here. Suppose I first choose what this picture on the left looks like, I choose what the picture on the right looks like, and I choose B. And only after doing that do I decide how long this path is. See, I can make this path longer by gluing these 2 points together, and subsequently gluing these 2 points together. Or I can make it shorter by taking this edge and cutting it and breaking it apart. Or taking the next edge in the chordal path and cutting it and breaking it apart. So it's fine to first choose the picture and then decide how much to zip up or zip down. And this suggests that in the scaling limit, when I focus on what happens near this point, I mean, having this was about just as likely as having this picture zipped up by one or unzipped by one. So which means that in the scaling limit, I would expect that whatever picture I get down here, it should be invariant under the operation of zipping up by a unit of quantum length or zipping down by a unit of quantum length. Okay, so we now have a set of criteria that we'd expect any scaling limit to satisfy. The curve should be independent of the metric. The left side random surface should be independent of the right random surface. The whole thing should be invariant under zipping down by a quantum length unit or zipping up by a quantum length unit. Okay, and what I'm constructing in this, and this thing should be an SLE2. Okay. So what I'm saying is the quantum zipper that I'm constructing in this week's lecture satisfies all these properties when you take the length invariant version. So, I consider these to be fairly compelling arguments, suggesting that this should be the right answer. I mean, you have a series of coincidences. It seems to have all the properties a scaling limit should have, but that's not a proof, of course. And it's even this question: do a random walk on this graph and show it looks like a Brownian motion on this graph. That's the first part of what needs to be done to. We have no idea. All of our our random walk in random environment tools are much more simplistic than anything that would work in a random walk on a random graph like this, where the randomness is sort of truly serious. It's not a perturbation of a lattice. So no proof, but well, okay. So any questions about this discrete story I'm telling you? Yes? In the case of random calculation, they have these rejections. Yes? That give access to random walks? That's a good question. So in the case of random quadrangulations, so in this case, really I'm choosing a random surface weighted by the number of figure 8 tree-like things on it. It was essentially a random surface weighted by the number of spanning trees. So it's a random surface comma tree pair, which is equivalent to first choosing a surface where the probability of each surface is proportional to the number of trees on it, and then given that, choosing the tree on that. And this should correspond to Louisville quantum gravity with gamma squared equals 2, and the path being SLE2. If I didn't weight by the number of spanning trees, I just took a uniform quadrangulation, then that is supposed to correspond to quantum gravity with kappa squared equals 8/3. Or sorry, with gamma squared equals 8/3. Kappa equals 8/3. And if I were to glue two of those things together, then the boundary should look like a self-avoiding walk. I can do this figure 8 where I don't put any stuff in the inside. So I don't have a tree, I just have a figure 8. If I do that, then this thing should be an SLE 8/3. Okay. Now this wasn't your question, but Your question was specifically what happens if we look at this Schaefer bijection, and what that essentially amounts to is looking at sort of a breadth-first search tree on your graph. So instead of taking a random tree here, I associate a very particular tree that depends on the graph structure. What is the scaling limit of that tree? Well, okay, that wasn't exactly your question, but that's one question you could ask, and I don't know the answer to that one. I don't have a good conjecture for what the scaling limit of that tree is. You know, what you asked specifically is, does this picture, this breadth-first tree, and the fact that they have such a nice, clean description of its law, does that help you in any way in understanding what a random walk on the surface they create should look like? And the answer is, well, it must be helpful, but I have no idea why. And as far as I know, nobody has any idea. I mean, basically they form a random surface by gluing together a pair of trees in a very canonical way, but how does that help you to find random walk on this glued together pair of trees? We just have no clue. So all these questions, random walks on random surfaces, this is a topic which we've made very little progress. I can tell you what progress there has been made. Omer Angel and Oded Schramm, so that if you take the infinite volume limit of the random triangulation and start a random walk on it, it's recurrent. Goes back to the origin infinitely many times. Okay? That's a statement. What's that? Was it the walk on the faces? Yeah, I guess it was the walk on the faces. That's right. So, because everything's a triangle, then it's three regular. They needed that. That's right. So that's a theorem. It's a nice result, but of course it's very far from saying that the walk is close to Brownian motion. The random walk is close to the Brownian motion. But maybe not impossibly far. Who knows? So the equivalent of a... What about Brownian motion? Is that recurrent? If I take the infinite volume limit, do a Brownian motion on a triangle, does it visit that triangle infinitely often? Well, in this case, there is some announced work by Stefan Roda and one of his students, I believe. I should remember the name, but I don't. But that claims that this Brownian motion is actually also recurrent on the infinite volume limit. Okay, well, this is something. I mean, the fact that Brownian motion is recurrent means that if you take the infinite volume limit, this is a random simply connected surface, that you can conformally map it to the plane, the whole plane, instead of conformally mapping it to a disk. Because remember, a simply connected surface, there are three types of geometry. There's the complex sphere, there's the complex plane, and there's the disk. And we know this thing is embedded in the plane, so we know it's either the plane or the disk, and they know it's the plane. They call it being parabolic instead of hyperbolic. Yes? Theorem 1 and Theorem 2. Yes, okay. So we have some impatience. Okay, let's move on then. Okay, so first, I'm going to define, I'm just going to start doing some Ito's formula calculations. So for the forward flow F SLE, what is that? So I have this function f sub t. It's this unzipping function, sending the tip of the curve to 0. And we did this. We know that df sub t z is 2 over ftz dt minus root kappa dbt. This is just the Loevner's evolution. And the reverse flow SLE is the same, except I replace the 2 with a minus 2. And then it's zipping up, whereas this one is zipping down. Okay, now I I compute, what happens if I take log of f sub t of z and I take d of the log of that? Okay, so, how are our Ito's formula skills? So, if I take d of the log of ft, what do? I take 1 over ft of z times dft of z plus, and then I take a second derivative, and then multiply it by dt term times the square of the bt part times kappa. So when I take the 1 over ftz times dt, that gives me, well, d ftz is 2 over this minus kappa over this. And that's going to give me, so that's going to give me this piece and 1/2 of this piece. So I had 1 over ftz times this. So I'm multiplying this thing by 1 over ft of z. So when I multiply this by 1 over ft of z, I get this. When I multiply this by 1 over ftz, I get the first half of this term. Okay, then when I take the second derivative, I get minus 1 over z squared times the square of this. Sorry, minus 1 over this object, ftz squared. And that gives me this second piece here. Okay, so hopefully that's okay. Then if I want to take ft prime of z, this means differentiate with respect to z. So differentiating with respect to z sort of commutes with differentiating with respect to t. So here I'm just going to take this guy and differentiate it with respect to z. And so that term goes away, and I get minus 2 over ftz squared times ft prime of z. And here, if I want to take d log of this, well, this thing here doesn't even have a bt term here. So this is not Ito's formula. This is just chain rule. So d of the log of this is just going to be 1 over ft prime of z times this. And so I'm taking 1 over ft prime of z, which cancels out the ft prime of z up here, and I get minus 2 over ftz squared dt. And on the right, it's exactly the same, but the signs are different. Okay? So these are the first things. And remember why these things were important. Right? When I take the argument of ft prime of z, that corresponds to this. That's just something that tells me the winding number, the winding. And if I take the log over here, that's just the real part over here. That's the thing that tells me the quantum transformation rule. Okay, so I've just computed those objects, and now I'm going to do some more computations. Okay, I'm just going to set some parameters. Chi will be 2 over root kappa minus root kappa over 2. Q will be 2 over root kappa plus root kappa over 2. And I'm going to define these two things that I'm going to claim are local martingales. So there's ht star, which is one linear combination of the log and the log ft prime, and ht star, which is a different linear combination of the log and the log ft prime. Now, if you look up here, you'll note when you look at the log of ft, d log ft, it had this particular term, something over ftz squared times dt plus something times dbt. And the d log ft prime was also something over ftz squared. So you can see if I take the right linear combination of this guy and this guy, then this piece and this piece will cancel. And so d of the appropriate linear combination of this guy and this guy will be just something times dbt. Okay, which means that the sum of log of this and log of this will be a local martingale. And here's the linear combination you take. I take ht star is minus 2 over root kappa log minus chi log ft prime. And over here I take 2 over root kappa log ft plus q log ft prime. Okay, and just checking the signs and everything, it works. Okay, now I take dht, and you see I get this nice form on both sides. Here it's 2 over ftz dbt. Here it's minus 2 over ftz dbt. And you know, I had some freedom in defining this martingale. I could have chosen any constant multiple of this, and it would still have been a local martingale. But I chose the martingale so that d of this would have this nice form. It doesn't depend on kappa. Okay, now, and now I'm going to define the martingales I really care about. On the forward side, I'm going to take the imaginary part of this martingale, imaginary part ht star of z, which corresponds to replacing these logs with args, argument functions. And on the right side, I'm going to take the real part of ht star, which corresponds to replacing these logs with the log of the absolute value. And now d of htz is the imaginary part of this 2 over ftz dbt, and dhtz on this side is the real part. Okay? Everything clear so far? Isn't it nice we're doing actual calculations instead of waving our hands at pictures? Okay. So now, well, maybe I'll wave my hands at pictures for a minute. If you just want you to understand what these objects are, dhtz and dhtz on this side. What is the imaginary part of 2 over ft of z? Well, at time 0, what is the ftz? You know, f0 of z is just equal to z. So what does the imaginary part of 2 over z look like? Well, okay, this is a nice function. And you think about its level sets are these circles that are tangential to 0. It's a function which is 0 everywhere along the real axis. And it blows up at this one point. Morally speaking, we think of this function as describing the harmonic measure of this point viewed from the boundary. You know, what's the probability that a Brownian motion starting out here hits this particular point? Well, of course, that's 0, but you could take that point to be a small interval and then look at the probability you hit that, multiply it by some constant so that as the interval gets smaller, you get some limit. So that's, we think of this just as being the harmonic measure of this point seen from the inside. And if I take imaginary part of 2 over ft of z, it will be similar. But now I'll have some curve, and I'll have these kind of circle things. You know, the conformal images of these circles when I map up to the complement of this curve. And this essentially tells me the harmonic measure of this point viewed from elsewhere. And because I'm thinking of h sub t of z as representing the conditional expectation of the field height, given what I've seen on the curve so far, it should not be so surprising that, you know, conditioned on what I've seen on the curve up to this point, when I start making observations down here, how does it change the heights everywhere else? Well, when I make an observation here, it adds or subtracts a small multiple of this function. Because whatever I do here, it's going to change the function in a way that's harmonic everywhere else, and 0 along this boundary. I'm just adding or subtracting a small multiple of this. Well, okay, what happens in this case here? I'm adding on this side. On this side, I'm taking the real part. And what does the real part look like? Well, that's a function which whose level sets are they're like this. It's 0 on this axis, and its level sets are circles. You know, I can extend all the way down here if I like, but its level sets are these semicircles here. And this function was 0 along the boundary. This function is not. It's 0 along this straight line. And if we think about it, and then I can conformally map. What happens if I take this conformal map? Well, I've zipped up, and I want to know what happens when I zip up a little further. Well, let's just imagine we're starting at 0. What happens when I zip up a little bit? How does that change my expected height? How does that change h sub t? And well, what it should be is, when I take this quantum random surface and I decide, how does this side glue to this side? And I say, does the initial path segment does it look like this? Or does the initial path segment look like this? If it looks like this, then what you see is that the harmonic measure of this piece is much larger than the harmonic measure of this piece down under here, which would tell me that before I zip up, it must have been the case that a fairly large piece over here was getting glued to a fairly small piece down here. And what this tells me is something about the ratio, or the difference between the field height here and the field height here. If this curve is 3 times as big as this curve here, then e to the gamma h over 2 should be 3 times as big over here as it is over here. And knowing that tells me what the ratio is between h here and h here, okay, on sort of an infinitesimal level. So that tells me something about the difference between h. So if I observe that, hey, h is a little bit bigger over here than it is over here, how does that change the expectation? Well, here it's positive over here, the function is negative over here. I'm basically adding or subtracting a small multiple of this function, which is 0 up here, positive on this side, negative on this side. So if I find out I'm gluing a small piece here to a big piece here, in my conditional expectation I'll modify by adding a multiple of this function. I find I'm gluing the other way around, then I find h must be bigger on this side, so I'll subtract a multiple of this function. Okay. So that's intuition, but I just want to point out these forms have very nice interpretations. They are what you would guess they would have to be. Okay. Now there's another calculation. C sub t of z, the forward case will be what I will call the conformal radius. And if you compute the conformal radius of a point in a half plane, you just find it has this form. So it's log of the imaginary part f sub t of z minus the real part of the log f t z prime. And if you like, don't worry about the fact that this has the name conformal radius. This is just a function that depends on f sub t and on z. And you do an Ito's formula computation will show you that d of the quadratic variation of h sub t with itself is just minus dct. And another way of saying that is that h sub t of z is a Brownian motion if you parameterize time in this way, by minus d sub t of z. So this minus d sub t of z, c sub t of z is strictly decreasing in time. It's the log of your radius, and your radius is decreasing as you see more of your path. And okay, so this is again an Ito's formula calculation. Oh, ht? It's this. It's the imaginary part of this guy. Yes. Yes, that's right. That's right. Yes. So Vendelin is pointing out that if you know about things like capacity from a point, that I'm drawing this path. C sub t is representing log C sub t is some sense the capacity of this point in the whole domain. So it's maybe it's sort of understood that as you grow near this curve, the rate at which the capacity changes should be determined, by the square of this function, this harmonic measure. So if you happen to know that fact from other sources, then that would give you one way of computing this without going through the Ito's formula derivation. Okay, so now let's do some more calculations. Okay, so now g of yz is the Green's function. You recall we computed this for the on the forward flow side. This is the zero boundary Green's function. And remember, it was log of y minus z bar minus log of y minus z. I hope everyone remembers that. And the reverse flow SLE, I'm going to set g of y of z to be the Green's function for the free boundary SLE. And you'll recall we computed that, and it was the same up to a sign. We got minus log y minus z minus log y minus z bar. So this is what we did by taking we knew the Green's function for whole plane SLE was just minus the log, and then we projected onto the even and the odd parts, and got the new Green's functions. And this was that simple argument where we ended up with these two guys. Okay, so now I'll define g sub t of y and z to be the Green's function of f sub t of y with f sub t of z. And I'll define g sub t of y of z on this side the same way. And let's compute d of g sub t of y and z. Okay, well, it's not that hard. I mean, so if I want to compute d of g sub t of this, I have to put my f sub t in here, and an f sub t in here, and just take d of this with Ito's formula. What is that? It's going to be 1 over this thing times, etc. So maybe I can just let you trust me that this calculation is straightforward. 5 or 6 lines. It's just Ito's formula. And same thing over here. You do Ito's formula, and you get something similar here, but it starts to look a little bit different because here you get an imaginary part, and here you get a real part. And now, what I can check is that if I take d of h sub ty with h sub t of z, that's minus d of g sub t y z. Now if I take d of h sub ty, h sub t of z, that's minus d g t y z over here also. So remember, this is the quadratic variation. Okay. So again, it's just a calculation. Right. Okay, and now, so this is all just straightforward Ito's formula. I didn't write down all the steps. I haven't done any real math in these calculations yet. But now on this next step, what I'm going to do is I'm going to find E sub t of rho. So rho will be some density. I'll think of it as some test function. To be the integral over h of rho y, g sub t y z, rho z, dy, dz. And I check that d of h sub t rho minus this quadratic variation is equal to minus d of e sub t of rho. And that's essentially, this is essentially just Fubini's theorem. Okay, so let me write down a picture to illustrate a little better what's going on here. So here's what's going on. And let's focus first on the forward SLE case. So I have over here a test function. A test function rho, maybe it's supported on this set here. Maybe these are its level sets. It's a little bump function here. I have this test function rho. And now I start growing my SLE path. Okay, at each time, I can ask, what is the expectation of my field H inner product with rho given the path up to time t? And what I claim is that this should be equal to H sub t, inner product with rho. This is sort of what I'm trying to show. Well, for now, just take this as a definition. You know, so let's look at this HT inner product with rho and try to see how this evolves in time. So this HT integrated against rho is some number that's varying in t. And we know that H sub t is pointwise of martingale. This is an integral of martingales. And so it is itself a martingale. You know, you have enough bounds on the that you need to see that this is itself a martingale. So so we have a martingale here. And I would like to ask, what is this martingale exactly? So it's a continuous martingale. It's a time change of Brownian motion. But it's a Brownian motion run at what speed? What's the parameter with respect to which this is a Brownian motion? And I claim, just a computation, the parameter is this particular thing, E sub t of rho. And what is E sub t of rho? E sub t of rho is this integral of rho y gt yz rho z dy dz. Okay, but we've seen this integral before, right? This integral tells me if I were to choose a Gaussian free field in this domain, which is the half plane minus this set, what would be the variance of rho integrated against that Gaussian free field? Well, it's the integral. It's this integral. So on any set, if I take a Gaussian free field on that set and a test function rho, the variance of the Gaussian free field against rho is this integral. Okay, so we computed that earlier. So now it's time to step back a bit and tell you what my general strategy is, how I'm going to use this information. So I have this way of constructing a field, which is first I draw the path, then condition on that, I take a Gaussian free field in the boundary. And another way of saying that is first I choose the path up to time t, and I take the field H sub t, and then I add H tilde, I add a Gaussian free field in complement. So recall what I'm always doing is saying, first choose ft, which determines ht, then take h equal to ht plus 0 boundary Gaussian free field on h minus gamma 0 to t. And I want to show field constructed this way is the GFF. I guess plus H naught. So I want to, this is what I want. And so I've given you this construction. I want to show you that that's the Gaussian free field. Well, okay, how do you do that? So first of all, let me tell you this construction is a distribution. It constructs for you an honest distribution. How do you prove that? Well, you prove that this H sub t is almost surely in L1. That's an easy calculation. So H sub t is nice as it can be. And anything that's in L1 is a distribution. So first you see that HT is a distribution. It's locally in L1. And then you check that if you take the free field restricted to a subset, that kind of also determines for you a distribution on the whole space, a generalized function. And that's done in this paper with Oded Shram that's also linked to from the PIMS site. So you know that this construction gives you a random distribution. But I want to show that the random distribution is the Gaussian free field. Okay, well, I want to think back. What would you do if I asked you to prove something was Brownian motion? Besides panic. I mean, probably one thing you might do is look at the finite dimensional laws. Because Brownian motion is, it's a Gaussian process, like the Gaussian free field. And if I look at its joint laws at a set of points, I mean, what determines Brownian motion? Well, the covariance of Bs with Bt is equal to the min of S and T. The mean of Bt equals 0. You know the means and covariances, so you know the law for any finite set of points. Does that determine for you the Brownian motion? Well, almost. I mean, there's some technicalities you would do in your first year probability class where, you say, well, this, if I only take a sigma algebra where I can look at finitely many points at a time, then statements like the Brownian motion is a continuous curve don't quite make sense. I have to talk about a continuous version or defining it on the rationals and extending continuously everywhere else or something. But if I give you a random continuous curve and I tell you, here's a continuous random curve, it has the same, if you look at the law at finite sets of points, it looks like a Brownian motion. Then you know it must be a Brownian motion. Okay, so that's so here. This is a similar thing, whereas instead of replace individual points here with individual test functions, individual rows. If I give you a distribution, continuous function on the rows, and you have to just check that the finite dimensional laws, want to integrate against row, it's what it's supposed to be. If I integrate against finitely many rows. Well, okay, and then there is still another trick that is even better. Here's a question. If I give you a Gaussian, suppose I give you a function or a random variable on R2, and I tell you that if you project that random variable onto any line through the origin, you get a unit variance mean zero Gaussian random variable. Does that mean that it's a Brownian motion that it's a Gaussian random variable on all of R2? What's that? That's the definition? Okay. So the French are not impressed. That's right. So I guess, certainly everyone here in France, and maybe the rest of you too, learned this in grade school. But the statement is that if I give you a random variable in R2, let's draw its probability density function, and I tell you that if I project that random variable along to any line, meaning I choose randomly from this and I project onto this line, I just integrate out the orthogonal direction. If I tell you that along every line when I do the projection I get a Gaussian random variable with variance 1 and mean 0, then that must mean that the law of the whole thing is a Gaussian random variable with variance 1 mean 0. And okay, you can check this by taking Fourier transforms. Use the characteristic function. The fact that it's correct when you project onto every line means that the characteristic function is what it is supposed to be. And that determines the law. Okay? So if I want to prove something is Brownian motion, I could say, well, take any finite linear combination of points, or maybe not necessarily finite, take any linear functional of the Brownian motion, and show that that the law of your random function integrated against that linear function, the law of that linear functional of your Brownian motion is what it is supposed to be. Okay, that does the job. So in our case, if I want to show that the field constructed in this way is the Gaussian free field on H, it is sufficient to show that for a fixed test function rho, the law of this field integrated against rho is a Gaussian with the right variance. Let me write that down. So it suffices for us to show that if I take the H constructed this way is Gaussian with mean H0 inner product with rho and variance E sub 0 of rho. So E sub 0 is this Green's function integral if you just take the half plane. Okay. But now what have I told you about how to generate this, how we're generating this rho? I'm saying as we're generating this rho, we're generating it in two steps. First, we're doing a Brownian motion for some random amount of time. This H sub t rho is a Brownian motion for some random amount of time. And let me, let's say we start at time minus E 0 of rho. So I do a Brownian motion for some random amount of time until we get to minus Et of rho. So that's the way this H sub t of rho evolves. Remember, H sub t is a Brownian motion when you parametrize time by minus E sub t of rho. That's what we proved. It depends on the Brownian motion. That's right. Yeah, that's right. So I'm running this up to a stopping time that depends on the Brownian motion. And it's a random amount of time. It's completely terrible, except when I get to this point, what do I do next? So the amount of time depends on the Brownian motion. When I get to this point, what do I do next? What I do next is I add the Gaussian free field on the complement of this curve. Right? And in that Gaussian free field, that field integrated against rho is a Gaussian with variance equal to E sub t of rho. So I run to this point, and then I say, now add Gaussian of variance E sub t of rho. And, well, adding a Gaussian of variance E sub t of rho is equivalent to just running the Brownian motion for the rest of the time. Ta-da. Okay, Wendelin is shaking his head. But this is sort of the crux of the argument here. Fourier transform. Yes. It's a crazy time. But I don't care what the time it is, because at that time, once I get to that time, what you're saying is you care about which parts of this curve are white and which parts are orange. And I say, I'm a colorblind person. I accept orange people and white people on equal footing. It doesn't affect the law of what you get in the end, right? I don't know. Any other questions about this construction? Just saying this H sub t paired with rho is a Gaussian process, which is a Brownian motion when you parameterize time by minus d by minus E sub t of rho. So I'm going to graph minus E of sub t of rho. Here's minus E0 of rho. I run until a random stopping time, which is minus E sub t of rho. And then I add a Gaussian whose variance is minus E sub t of rho, which is just drawing the rest of the curve. And where I stop along this thing and change from white to orange is random. But still, the Brownian motion itself, what I get at the end, doesn't care. It's a cute trick. Okay, and that's really it. And this reverse version is exactly the same, except that we change a bunch of signs. But again, we take rho to be a test function. In that case, it's a here E sub it's a test function. It has to have mean 0, but that's okay. So rho is some test function whose total integral is 0, and we have this E sub t. We can take rho to be smooth if we like, and we have some E sub t. It's a Brownian motion. When you parameterize by minus E sub t, when you get to the end, you add this integral, which is what you're supposed to add. It's exactly what you get when you take the Gaussian free field on one side and pull it back to the other. And, okay, voila. Okay, I don't know. I hope this is satisfying. But maybe I'll take a couple questions about this and then end. So this, if you believe me, up to, there are a couple little details you need to check to see that, your stochastic Fubini theorem goes through, but they're all sort of pretty easy. Okay, there they are. Essentially you want to show that this plus this is a martingale in order to get the thing actually being a martingale, and you have really good control on the variances and everything. So, basically to say the integral of a martingale integral of martingales is a martingale. You need to check something. But that something is easy. So essentially, we've done all the calculations. So, a question about? Yes? Okay, so remember, what's our construction of H? Our construction of H is, we start with H0, and we draw this path, and we generate from that this H sub t. Second, given H sub t and this path, we add a Gaussian free field in the half plane minus this path. So we have two things we're adding together. One is this H sub t. The second is a free field on the half plane minus the path. And now I'm going to focus on HT inner product with rho. So now the two things I'm adding are HT integrated against rho. I'm going to add that to this free field in the plane minus the slit integrated against rho. Okay, this free field in the domain minus the slit integrated against rho is a Gaussian random variable conditioned on the path. It's a Gaussian random variable whose variance is E sub t of rho. And that's what I kind of represent by the difference between this value and this value. That's a Gaussian whose variance is this length. And this length is E sub t of rho. So I think of this, the change during the orange segment is equal to rho integrated against this zero boundary Gaussian free field on the half plane minus the slit. The change in this motion during the first segment is equal to H sub t of rho minus H sub 0 of rho. So as t moves along, this H sub t of rho does a Brownian motion with respect to this time, the time being minus H sub t of rho. And then it stops at some random stopping time. And then I continue in orange. I don't know, did that help? What's that? Okay. Well, maybe there's another question that could help clear up what's still. I mean, it's. Essentially, I have a Brownian motion that's colored white and orange, and I'm saying, start your Brownian motion, color it white at some random stopping time, change the color to orange, but it's still a Gaussian at the end. Yes?
So with this argument, for example, you just use a random stopping time for
A random stopping time for the SLE? Yes, you can use any old stopping time you want. So I said we're going to take, we're going to run SLE up until a fixed time. And I just did that because I thought it made the theorem statement a little bit cleaner. When I wrote it with a stopping time, it filled up a little more space on the page, and I didn't like the way it looked. But yeah, there's nothing in this argument that you can run this up to any stopping time. And for that matter, you can run your, if you want to, you can run your SLE all the way to infinity. And then this E sub t of rho will be E infinity of rho, which if your Brownian motion is not space-filling, that will still be less than, it still won't get you all the way to here. It still will be greater than 0. But yeah, you can run this up to any stopping time and then change color to orange. And you'll still have a Brownian motion at the end. And again, so this change color to orange, I know this is confusing, so let me say this one more time. It's where this object here is a Brownian motion parametrized by minus the energy, minus E sub t of rho. So as I observe more of this curve, this e sub t of rho is an decreasing function. So minus e sub t of rho is an increasing function. If I take that as my notion of time, this is just a Brownian motion. So I'm going to do this for some time, and then conditioned at that time, I'm going to add this free field to the complement. And this free field to the complement integrated against rho is a Gaussian of variance, e sub t of rho by definition. You know, that's how I kind of defined e sub t of rho. So that the variance of the Gaussian free field integrated against rho in this domain, half plane minus curve up to time t would be this. So then I add something with variance e sub t of rho. And adding something with variance e sub t of rho is equivalent to running a Brownian motion for time e sub t of rho. Okay. Maybe I can take one more question and then lunch. Or maybe now it's clear. Maybe the mention of lunch just sort of cleared everything up. Okay, thank you.